Okay, so hopefully you guys are feeling pretty good about the states of matter. And tomorrow we will have a Kahoot on the states of matter. And then pretty soon, I think maybe Thursday, we'll do a quick little Google form checkup on it. But there's one more thing that I want to talk about, because this is kind of what determines what state of matter something is in. So now that you know the characteristics of the states of matter, here's what puts or makes something be a solid, a liquid, or a gas, right? So there's this theory called the kinetic molecular theory of matter. Sounds like super intense. It's not, right? Sounds fancy in a lot of words, but it's actually kind of, it makes sense, it's kind of logical. Obviously we know that all material is made of particles, whether you want to call them atoms, molecules, which we learned yesterday was little lumps, right? Or those ions, if you're talking about having a different number of electrons for the normal version of the element. Whatever you want to call it, we know that matter, all things are made of tiny particles, tiny stuff, right? So that's kind of what we're going to be looking at. We're looking zoomed in, like at the small molecular level, what's going on. Because obviously, if you see water, you see an ice cube, you see a glass of water, and then you see steam, it's pretty easy to tell which one's a solid, which one's a liquid, and which one's a gas. That's not really what this unit's about. It's more looking deep into like what makes that a solid, a liquid, or a gas, right? And so one thing that you might not realize is that everything all around us, even if it looks visibly perfectly still, like my mouse, right? Doesn't look like it's moving. It actually, the molecules that make up that mouse are shaking, vibrating in place just a little bit. Everything is. Even if it doesn't look like it's moving, at the molecular level, it is. Right? And so we know that solids can move just a little bit in place. Liquids can move a little bit more, and then our gases, they're like the wild child, right? They can like bebop and move and slam around all over the place, right? And so the third idea that goes with this kinetic molecular theory of matter is that these molecules, when they move, they're able to collide with each other, they collide with the walls of the container. And so, again, that's just kind of common sense. Like, if something's moving, well, then, yeah, it has the opportunity to hit into something else, right? And that's all this means, right? And then the fourth idea, this is the one. Something's weird with this slide. There we go. And this is what I said is the key behind basically this whole unit. How tightly packed the molecules are and how strongly they're bonded will determine what state of matter the material is in. That's one big idea, right? So how close are they? Right? Well, they're packed in here pretty tight. That's what makes these kind of symbolizing our solid, right? When they have more space between them, liquid, even more space, that's symbolizing our gas, okay? Oh, geez, here we go again. And so the final thing that is kind of a new idea is the connection between the kinetic energy of something and temperature. Somebody tell me, what does kinetic energy mean? It's the energy of what? Last year we talked a lot about the potential energy. Change your mind?
I would say like motion or something.
Yeah, absolutely. Kinetic energy is motion. Last year we had the whole unit on potential energy, which is the energy of position or like stored up energy, right? This year we're going to talk a lot about potential, but also kinetic, which is motion, right? And so basically things are moving between those two. You know, you either have potential to move or you're actually moving, right? And so it's kind of like a flux going back and forth between the two. And so that's kind of what we're going to focus on for towards the rest of this unit. But the idea that kinetic energy or motion of the particles is directly proportional to temperature. So when we say directly proportional, what does that mean? So like, if the temperature goes up, what does that mean for kinetic energy?
It also goes up.
Good. So if kinetic energy goes down, what's that mean for temperature? I see some of you going like, go down, right? Yeah. So directly proportional means they're going to do the exact same thing. So they're like besties. Whatever one does, the other's going to do, right? And that, What's that noise? And so that is the last piece of this whole kinetic molecular theory of matter. Okay, so the relationship between motion and temperature obviously is like hand in hand. If they're proportional, they're going to do the same thing. So to increase something's temperature, what you're really doing at the molecular level is you're increasing the motion of those molecules. Can we visually see it by watching this mouse? No, right? It's happening internally, like at the molecular level where you can't see it with just your eyeballs, right? And so that's one thing that sometimes people are kind of like, it's kind of weird. Like, obviously we know we can't physically see. I'll show you some videos like where they actually like graph the temperature, and as the temperature's increasing, you can actually kind of see the melting process starting. So we're gonna show this, but again, try not to overthink it. Just as one goes up, the other goes up, and as one goes down, the other goes down. All right, so here's the thing. Particles are gonna vibrate and move more and more quickly as matter is heated up. Think about yourself, all right? Always kind of refer back to something that you understand or have had experience with. Well, when you're running around, you get hot, right? Makes sense, right? Molecules are the same way. The more they move, the hotter they get. So if you heat them up, you're gonna also cause them to move. Right? And so if the opposite's also true, when you're cold, right? You kind of like come in on yourself and you're like, oh, right? Usually if you're cold, a lot of times you're not moving. Like if you're sedentary, like sitting watching a movie, playing video games, maybe you get chilly and you put on a sweatshirt or you get a blanket or something. You know, the more still, a lot of times, the less you feel warm, okay? All right, so temperature is really just a measure of the average kinetic energy. And this is a different way of thinking. This is like science talk, not like what we, like if someone says, what's the temperature gonna be? You're not like, ooh, I wonder how fast the molecules are moving today. Well, that's really what it is, but we don't think of it that way, all right, in our everyday life. But in science, what it means is how much is that substance moving? How fast are those molecules moving? And so any change in temperature is going to have a direct effect on the kinetic energy. So if the temperature is going down, then the motion of the molecules is going down. If the temperature is on the rise, well then the motion is also on the rise for those molecules. Right? And so obviously adding or removing heat, which the fancy science name is thermal energy, from that molecular motion is the #1 way to change something from one state of matter to the other. So I can, when we did the solution example with the Kool-Aid, well, I had room temperature water and Kool-Aid mixed, and then I put it on the hot plate. I was changing it from a liquid, adding heat to it, caused the molecules to move around more and turn into steam, which is the gas version. So I was able to change it from one state of matter to another by adding heat, right? And so that is one phase change called evaporation. Something else that's kind of nice, as you look at like water boiling, like you actually see the bubbles. You see that liquid water have motion. So not only are the molecules themselves moving, but you can visually on the outside see the motion. And so sometimes that kind of helps if you can visualize that. All right, here's something that's super important. Look at the size of these little spheres. I think I have. So, like this one is the same size as this one, right? All of these are the same size. When they're cold, look at the space between them. They're closer. When they're hot, it takes 2 fingers, right, in between. So when they're cold, typically matter will come together or constrict, okay? It comes in. Just like when you're cold, what do? You like spread out and you're like, oh, I'm so cold. Like, who does that? That's weird, right? When you're cold, you're like, right? That's what most types of matter will do. The molecules come closer together. Now, the molecules themselves whether they get hot or cold, are not expanding or contracting. Okay, so the molecule size is staying the same. So my marble is still a marble. It doesn't matter if it gets hot or cold. But what's actually happening with all the molecules is maybe they come closer together, or maybe they expand a little bit. All right? And so that's what's actually happening to the molecules. The space between them is changing as they go from cold to hot or hot to cold. Same thing like when you're hot. You're not like, whoa, I'm so hot. What? Like if you did that, somebody would be like, do you understand what hot means? Like that doesn't make sense. So a lot of times people will think, oh, the molecule itself is shrinking or the molecule itself is expanding. And that is not the case. It's just the space between them. So here to here, okay? And so that is a real common misconception, that the molecule is expanding or contracting, when really it's just the space between them that's changing. Okay, so most materials are going to contract when they're cooled, which means come together, and they're going to expand when they get hot. That's pretty normal. Okay, right now, because our temperature is so wonky, right? It's like 10 degrees this morning. You know, it was just like mid 30s, 40s the other day. Like our temperature goes up and down so much. I know like a lot of times like our houses like start to creak, you know what I mean? Because like the materials that build our houses, you know, like, and when it gets really cold, it all kind of contracts a little. And then as it starts to warm up, it kind of starts creaking because it expands, and then it gets cold again and it contracts. And so there's that natural play, because we understand like you can't stop this contracting and expanding process that matter goes through. And so if you hear your house creaking around, like when the temperature is pretty extreme, that's why, okay? Okay, yeah, come together, push apart for the expand. You guys with me so far? Yeah, okay. All right, so again, solids are gonna do this, liquids are gonna do this, and again, it's the size of the particle that stays the same, it's just the space between it. So here it shows, it has like this little adjustable kind of like stopper to it. And so as it starts to get heated, you can see the liquid has some space between it, but then when it gets really hot, you can see that it allows this to scooch up, and it actually has expanded and it's taking up more volume now, right? The molecules themselves are still the exact same molecules. Those molecules are not changing. All it is the space between them and then how much it is they're moving. Same thing here. You put it on a Bunsen burner, this beaker that had an original volume of a liquid here. Once it gets heated up, now it's taking up more space. So you can see it with the gas, you can see it with the liquid. It's a little bit easier. We'll watch a video that shows this with solids too, but sometimes it's harder to kind of see it with solids. Okay. And so, if you've ever noticed, like on a bridge, there are these things, they almost look like a zipper. Those are called expansion joints. There was, gosh, it was years ago now. There was a student, and his dad, I don't know like what company he worked for, but he helped build bridges. And there had been a big, like, I don't know, like something went wrong with the bridge. And they had to go and fix it and build a new bridge like down in West Virginia or something. It's like one of those big ones that goes over, I don't even know what river or anything. It's been so long, I can't remember all the details. But he said that they were talking to his dad, and they're like, one of the things, like the expansion joints had messed up on the existing bridge. And so what happens is you have these joints that allow that bridge to move, because let's face it, if we know that materials are going to contract when they get cold and they're going to expand when they get hot, and you're building a bridge in a place where the temperature changes a lot, like, oh, I don't know, most of the country, you have a big variety of temperature change, you're going to have to account for that. So if you have just a solid piece, it's going to experience stress, and eventually when it needs to contract, it's going to maybe buckle. right? And you can kind of see that here with this railroad. If it needs to expand, eventually it's gonna pull and there's gonna be little cracks. It's gonna have weaknesses, and then eventually over time, it's going to eventually break or like totally crack, right? And so these joints allow for that natural contracting and that natural expansion. And so again, it's just one way that we use what we understand about science to help make things that are safe, make things that are convenient, because it's not practical to be replacing bridges all the time because they crack under the stress of changing weather or changing temperature, right? Again, we're gonna watch a video that's gonna show some of this. And like even this concrete barrier, right? Like if you don't have some natural kind of places for this contracting and expanding to take place, it's gonna crack, it's gonna break. And then that becomes an issue. Okay, so looking at gases, and a couple of these videos are gonna show this, but this is how hot air balloons work, steam engines work. When things are cold, they're coming together. When they get heated up, they expand, and we use that expansion. And we also know that hot things are going to rise, which is like in a volcano, why that hot air is going to be coming out of the volcano. As it expands, it gets less dense, and so it's going to move upwards. Showing the same thing here, like here's your original volume of gas, and then it gets heated, and with that balloon on it, it's trapping that and not letting it move or leave the area. And so you can see that now it's expanding and filling up not only the bottle, but the balloon also. Okay. Anybody, we've been saying all along, think of water. We are around water all the time. Water, we see it in the solid, the liquid, and the gas phase, okay? Anybody question when I'm saying that things will normally contract when they're cold and expand when they're hot? That seems backwards if you think of water. What will a water bottle do if you fill it all the way to the top and you seal it up tight so it's almost overflowing and you put it in the freezer? Is it going to contract and shrink in? What's it going to do? It's going to expand. So I just told you that when things get cold, they come together. But we all have experienced water that freezes that will expand, right? So there is something special about water, and it's going to actually behave the exact opposite of most other forms of matter. And so what happens is because of its molecular like arrangement, the two hydrogens with the one oxygen. And so we have a video that we'll watch that'll kind of explain this, but we call this strange abnormal behavior of water the anomalous expansion of water. Because typically, like if you think of a glass of ice water, where are the ice cubes? Are they at the bottom or are they at the top? Top means less dense, right? They are less dense than the water that they're floating in. And so if you have a solid, solids typically are going to be more tightly packed. So why would something more tightly packed be less dense? So when you start trying to think about it logically, it's hard to make it make sense. And so the reason why is because those water molecules, if this is like my two hydrogens and this is my oxygen, H2O, they're going to kind of form little rings, and it leaves an opening in the center when these molecules come together tightly packed as a solid. And so it kind of leaves like a hollow circle when these molecules are connected. And when that happens, it actually makes it buoyant and causes it to float because it's less dense. It's taking up more space than when those molecules can just like slide in and fit next to each other as a liquid. And again, we'll watch a video that kind of shows this. But unfortunately, this happens, over Christmas time when it got so cold. People were having trouble with, things freezing up outside. If it gets down like to 30, 40 below, sometimes you even have to worry about like pipes freezing and busting on your house. Can you imagine like walking into your garage? Apparently they had water lines in their garage and it must have gotten cold enough and the pipes burst because the water froze and expanded, and then the water supply was coming in behind it and then just coated. That'd be a really, really bad scene. This is kind of showing, right? And so if it cracks because it expands and the water is still flowing, well then it's going to keep flowing and it's going to go out that crack. Same thing happened, that must have been a fountain. We talked about frost wedging last year, that weathering, component, which right about now, this time of year, our roads are getting really bad because we have a lot of that freezing thawing going on and a lot of moisture. So you have that water that's liquid, at night it freezes when it gets colder, that's gonna expand, and then in the day when it heats up, it's gonna melt, and then it's just gonna keep continuing to weaken that until this nice blacktop eventually kind of looks more like this. And that is an issue. So most of the time, logically, we understand that solids are gonna be more dense. They're more tightly packed, right? Like, this is really dense compared to, get rid of some, maybe the liquid version, right? There's a lot more space between them, it's not as tightly packed. So when you're like, yeah, more dense, solid, gonna come together, typically that would sink. Water is the huge exception to this rule though. And it all has to do with the molecular structure of the H2O molecules. This is why icebergs float and they're not buried at the bottom, because they're just like an ice cube. They're less dense than the water that they're floating in, and so they're gonna rise to the surface or stay at the surface, right? And so the heavier, warmer water is gonna be at the bottom, and the colder and less dense water and ice is gonna be at the top. And so this is what it looks like. So as a gas, the water molecules are all over, right? As a liquid, they are not connected. Once they become a solid, and you can kind of see that here, the red is the oxygen, the white is the two hydrogens, it almost forms like these little circles, right? So these two hydrogens and this oxygen are going to kind of connect with this hydrogen, this oxygen, and so you get, and if you look at this, you can kind of see what snowflakes look like, right? And so this is kind of what happens when you're looking at a solid. This is as a liquid, they're only weakly connected, like maybe with one hydrogen to another hydrogen. And so they are not set and rigid. And so like they are fluid, they're not set where they have to connect all the way. The gases, those water molecules are not connected to any other gas or any other water molecule at all. So no connection, a little connection, and then totally connected for our solid, liquid, and gas. But because of this, it leaves this opening in the center, making it less dense, right? So it's just a weird thing with the covalent bonds of the water molecule that cause this to happen. And again, most matter is not going to do that. It's just gonna pack in tightly and become more dense, right? So water is gonna be the oddball. So it's a great example for most of the things we talk about, and then it's a perfect example of the exact opposite when we're talking about expanding and contracting. Again, just another way to look at it. It's the hydrogen bond between these water molecules that cause this to happen. So here you can see the big opening, kind of the opening here, was kind of showing almost three-dimensionally these water molecules connecting, and then you see it starts to melt and you only get a few connections, and then it's totally melted. And so maybe you're looking at like the gas version over here because there's no connections between those water molecules, no attraction. Okay, okay, let's go back. We have some videos that we need to take a look at.